Imagine handing a brand new, highly enthusiastic intern the keys to your company's AWS account.
Oh boy.
Yeah, right.
Yeah.
Tell them to go fix a bug, you pat them on the back, and you just walk away
A recipe for disaster.
completely.
Yeah.
And then 11 days later, you log back in and discover they have silently racked up a $47,000 API bill
And let me guess, without actually fixing the bug.
without fixing the bug at all. And the craziest part is this is not a hypothetical scenario. That actually happened to a development team who let two AI agents talk to each other without proper supervision.
It's a really sobering reality check, because traditionally writing software was, well, it was like building a mechanical clock.
Right, very predictable.
Exactly. You machined the gears, you slotted them into place, and the logic executed deterministically. It did exactly what you programmed it to do. But when you step into the world of production-grade AI agents, that determinism just vanishes.
It's totally gone.
Yeah, you are no longer building a clock. You are managing a team of brilliant, highly capable, but entirely unpredictable digital workers.
Which really means if you're building in this space right now, you have to fundamentally shift your mindset.
You have to.
You are no longer just a developer prompting a model to, see if it can write a poem. You have to act like a seasoned tech consultant. Your job is architecting a reliable, cost-effective, and secure ecosystem.
That's exactly it.
And that's what we are unpacking in this deep dive today. We're looking at the architecture of production-grade AI agents, specifically focusing on the new Claude Agent SDK and the Agent Skills Open Standard.
Which is such a massive shift in how we handle this stuff.
Totally. So our mission today is to figure out how to build these systems efficiently, debunk a very persistent industry myth about why we use multi-agent architectures, and figure out how to secure our infrastructure against some truly terrifying emerging attack sectors.
And, the foundation of all of this starts with a very simple consulting principle, which is stop reinventing the wheel.
Right. Because building this from scratch is a nightmare.
It's incredibly complex to run autonomous agents safely. You have to handle tool execution loops, manage shrinking context windows, and build guardrails against infinite loops. Attempting to build that infrastructure from scratch for every single project is it's a recipe for catastrophic failure.
And that is the exact problem the Claude Agent SDK is designed to solve.
Exactly.
Looking at the underlying architecture, it's clear this isn't just a lightweight wrapper. The SDK is built directly from the battle-tested infrastructure of Claude Code.
Yeah, they brought the heavy machinery.
It really did.
Yeah.
And what stands out immediately is that it operates on a very specific assumption. It assumes your agent is working on a project. It assumes the agent needs to interact with files, navigate directories, read code bases, things like that.
And that project-level assumption changes everything about how the framework is designed. Because it assumes the agent needs to navigate a system natively, the SDK comes out of the box with built-in tools.
Like what kind of tools?
Tools like bash, read, edit, glob, and grep. You are essentially giving the agent a virtual pair of hands to operate a computer the exact same way a human engineer would.
Okay, just to clarify, for anyone who doesn't spend their entire life in a Linux terminal, when we talk about glob or grep, we're just talking about standard command line utilities, right?
The basics.
Like glob is for matching file paths, and grep is for searching through plain text data sets for lines that match a regular expression. So we are giving the agent basic operating system reflexes.
Yeah, and add native bash execution to that list.
Yeah.
And the capability jump is just massive. Having bash available means the agent can execute shell commands, run its own Python scripts, or use external data parsing tools like JQ.
Oh, JQ is great.
It's so useful. It's a lightweight command line processor for JSON. So if the agent encounters a massive, heavily nested JSON file, it doesn't have to read the whole thing into its context window.
Because that would eat up all your tokens.
Exactly. You can just write a quick JQ command in the shell to extract the one specific value it needs.
But giving an agent hands to type commands isn't enough, right? You still have to give it specialized knowledge so it actually knows what commands to type.
Right. Otherwise, it's just guessing.
Yeah. And looking at Anthropic's new open standard, this brings us to the concept of agent skills. Now, when most people hear the word skill in AI, they probably think of a system prompt.
Something basic, yeah.
Like, you are a helpful data analyst. Please format your output in Markdown. But this standard defines a skill as something much more robust than that.
Oh, yeah. Think of an agent skill as a portable, version-controlled folder. At its core, yes, there is a file called skill.md, but this folder bundles together deep procedural knowledge.
So it's not just a prompt.
No, not at all. It contains step-by-step instructions, executable shell scripts, API definitions, complex data templates. If you put on your tech consultant hat for a second, you should frame this as handing a comprehensive onboarding guide to a new hire.
I like that analogy.
Yeah, you are making a generalist foundation model and injecting it with deep domain-specific expertise.
Let's follow the logic there, though. Because if we are injecting all this deep expertise, like pages of instructions, Python scripts, JSON templates directly into the agent's brain, aren't we going to completely blow up the context window?
That is the big question.
Because we pay for every single token. If I have 50 different skills available for my enterprise agent, loading all of them at once would cost an absolute fortune before the agent even answers a user's prompt.
You're completely right. That token bloat is the exact architectural bottleneck that destroys the ROI of most early enterprise deployments.
So how does the SDK handle it?
It solves it through a mechanism called progressive disclosure. It's an incredibly elegant way to manage token costs while maintaining a vast library of deep knowledge. The framework essentially operates on 3 distinct levels of disclosure.
Okay, so level 1 is just the metadata and description, right?
Right. Level 1 is always loaded in the system prompt, and it costs almost nothing, maybe, I don't know, 30 tokens per skill.
Basically free.
Pretty much. It's essentially a directory. It tells the agent, hey, I have a skill for processing healthcare PDFs, and here is a 1-sentence description of what it does. The agent just knows the capability exists.
So if the user asks a question about parsing an invoice, the agent just ignores the healthcare PDF skill.
Exactly.
But if the user uploads medical records, then we hit level 2, which is the instructions.
Yes. The moment the agent's internal routing logic matches that level 1 description to the user's intent, level 2 triggers. The full skill.md instructions are dynamically injected into the active context.
Got it.
This alters the agent's execution state. It might grant the agent temporary permission to use specific medical parsing tools, for example.
And then we have level 3, which contains the heavy resources and scripts.
Right. Those heavy assets, the massive Python scripts, the 1,000-line JSON templates, those are strictly cordoned off. They are only loaded if explicitly called for by the level 2 instructions. The agent reads the file just in time, executes it, and then can drop it from its active memory.
Oh, wow. So it's very much like lazy loading a massive, complex web page.
That's a perfect way to look at it.
Yeah, like if you build a modern website, you don't force the user's browser to download a heavy 4K video asset the second they hit the homepage.
Right, that would be terrible design.
You preserve bandwidth by waiting until they actually scroll down to the video and click play. Progressive disclosure does the exact same thing, but instead of bandwidth, you're preserving the context window.
And taking that lazy loading analogy a step further, by not loading level 3 until it's explicitly requested, you also drastically reduce the chance of model confusion.
Oh, interesting. How so?
Well, the more irrelevant instructions you put in a prompt, the higher the chance the model hallucinates connections that don't even exist. So progressive disclosure keeps the context pristine.
That makes a lot of sense. So now that we have a highly efficient way to give a single agent specialized knowledge, the natural progression for any enterprise architect is figuring out how to combine multiple agents.
Yes, multi-agent systems.
And digging into the research on this, we run into one of the biggest misconceptions in the AI space right now. There is this pervasive industry belief that multi-agent architectures are fundamentally designed for speed.
Yeah, I hear this all the time.
The logic goes, if you throw 10 agents at a complex coding problem, they all work simultaneously in parallel, and the job gets done 10 times faster.
Which is a complete myth, especially for right-oriented tasks like software engineering or complex data modeling. I mean, both Anthropic and Cognition. The makers of the dev and coding agent, they have independently reached the exact same conclusion in their production testing.
Which is what?
If you take a sequential task with tight dependencies and try to parallelize it across multiple subagents, you don't get speed. You get a massive architectural headache.
Yeah, the documentation actually compares it to a game of telephone. Let's
Right.
walk through why that happens. Say Agent A writes a piece of back-end logic. It hands that code to Agent B, whose job is to write the unit tests. But Agent B doesn't have the implicit context of why Agent A made certain design choices or ignored a specific edge case.
Because they're isolated.
Exactly. So Agent B hallucinates a fix to make the test pass, altering the original logic. Then Agent B passes it to Agent C to deploy. The context just completely collapses.
And because the context collapses, the agents have to spend hundreds of thousands of tokens talking back and forth, trying to debug the very errors they introduce to each other.
Just a downward spiral.
Totally. The accuracy plummets and the API bills just explode. The data shows token costs spiking by up to 15 times compared to a normal, single-agent continuous chat.
Paying 15 times the token cost to get worse results is a pretty fast track to getting a project canceled.
Yeah, definitely.
But I do want to challenge this for a second. Looking at Anthropic's own internal research, they cited a 90% reduction in complex research time by using a lead Opus agent that delegated to a swarm of Sonnet subagents. Doesn't that directly prove that multi-agent architecture is about speed and parallelization?
So this is a critical distinction that separates a junior developer from a senior architect. Speed is a byproduct of multi-agent systems, but only for read-oriented, breadth-first tasks.
Okay, read-oriented.
Yeah, if your objective is research, say, analyzing 100 different company earnings reports to find mentions of supply chain issues, those tasks are completely independent of one another.
Right.
The subagent analyzing Apple does not need to know what the subagent analyzing Microsoft is doing. Parallelization works beautifully there. But the moment you apply that horizontal parallelization to sequential, right-oriented tasks, where step 3 depends entirely on step 2, you are burning money.
Okay, so if it's not about speed for those complex dependent tasks, what is the actual value of spinning up a subagent?
The true consultant-level value of a multi-agent architecture is context compression.
Context compression. Let's explore the mechanics of that. How does it work?
Consider an agent tasked with finding a specific vulnerability buried deep inside a massive legacy code base. If your main front-facing agent attempts to do that exploration itself, it pulls tens of thousands of tokens into its working memory.
It's loading all these files.
Right. It searches directories, hits dead ends, reads the wrong files, tries different grep commands. Its context window gets bloated with all of that trial and error, and it starts losing track of its original overarching goal. So a subagent's job is to take on that messy exploration in an isolated sandbox.
It does the dirty work. It spins up, burns 50,000 tokens, searching through files and getting errors, but it doesn't pollute the main agent's memory.
Precisely. And when that subagent finally locates the vulnerability, it doesn't send the entire messy log of its search history back. It returns a distilled, highly condensed 1,000 token summary of the exact file path and the problematic code snippet.
Oh, that's smart.
The main agent receives the answer, its context window stays pristine, and you prevent the primary model from getting confused by its own vast trail of trial and error.
There's actually a specific production pattern detailed in the research that utilizes this compression beautifully. It's called the router plus specialist pattern.
Yes. This is one of the most highly recommended architectures for enterprise deployments. You place a cheap, incredibly fast model like Claude at the front door of your application.
And it just directs traffic.
Exactly. Its only job is to act as a routing layer. It evaluates the incoming user request. If the request is simple, like summarizing a short text, Haiku handles it immediately. But if the request requires deep, specialized expertise, Haiku packages the context and delegates it to an expensive, highly capable specialist model like Sonnet or Opus.
Which means you aren't paying premium Opus prices to handle Haiku-level basic queries. You're reserving your most expensive cognitive resources for the hardest problems.
Right.
Implementing just that one routing pattern can reduce overall token costs by 40 to 60%.
And it actually improves reliability, too, because the specialist model starts with a clean, perfectly formatted prompt delivered by the router, rather than dealing with the messy, ambiguous input of an end user.
Compressing context and saving 60% on API costs is fantastic. But compressing context also means you are hiding steps. You have subagents doing thousands of invisible actions in the background.
That's the trade-off, yeah.
And when an autonomous system goes off the rails without human oversight, the blast